Welcome to this lecture on algebra. Today we are going to explore a fascinating and fundamental concept called row rank and column rank. If you have ever wondered how we measure the true amount of unique, non-redundant information hidden inside a matrix, you are in the exact right place. Let us dive in and build our understanding from the ground up. To start, imagine you are managing a team of 5 workers building a house. 2 are highly skilled and original, while the other 3 simply copy them. Even with 5 bodies on the site, your truly independent workforce is just 2 people. In algebra, a matrix is exactly like this team. The rows and columns are the workers. Sometimes a row is just a direct copy or a simple combination of others, bringing no new mathematical information. Rank is our way of counting the truly independent workers. Now that we understand the intuition, let us define this formally. We use the term linearly independent for a set of items where none can be created by mixing or scaling the others. If we look at the horizontal lists of numbers in a matrix, the maximum number of linearly independent rows is called the row rank. Similarly, looking vertically, the maximum number of linearly independent columns is the column rank. Simply put, if you cross out every redundant row or column, what you have left is your rank. This brings us to one of the most beautiful discoveries in linear algebra, the rank equality theorem. It states that for any matrix, regardless of its shape or size, the row rank will always exactly equal the column rank. It feels almost like magic. The rows and columns are completely different lists of numbers, yet they always contain the exact same amount of unique information. Because these two numbers are always identical, we usually drop the words row and column and simply call it the rank of the matrix. Let us look at the mathematical expression for this theorem. The formula is beautifully simple. R row equals R column equals R. Here, R row represents the row rank, which is the number of independent horizontal lists. The symbol R column represents the column rank, the independent vertical lists. And R is the final, unified rank of the matrix. If the row rank increases, meaning we add a new independent row, the column rank must increase by the exact same amount physically. They are perfectly locked together, ensuring the matrix's information is balanced. Before we prove why this theorem works, let us see it in action with a concrete example. We are given a 3 by 3 matrix A and we want to find its rank by simplifying it into a staircase pattern. Looking closely at the numbers, we might notice that the second row is exactly twice the first row. To eliminate this redundant information, we subtract 2 times the first row from the second row. When we do this, the entire second row becomes zeros, proving it brought no new information. Continuing with our matrix, we need to finish creating our staircase pattern, known as row echelon form. We push the row of zeros to the very bottom by swapping the second and third rows. This gives us our final simplified matrix R. Now we simply count. There are exactly 2 non-zero rows, so the row rank is 2. The first non-zero numbers in these rows, called pivots, are in the first and second columns, so the column rank is also 2. The final answer physically represents 2 independent dimensions. Let us look at a visual representation of the simplified matrix we just found. On the screen, you can see the matrix in row echelon form. Notice the staircase pattern highlighted. The non-zero rows are clearly marked, showing a row rank of 2. The leading non-zero entries, circled in red, are our pivots. They sit in the first 2 columns, visually confirming that our column rank is also 2. This diagram perfectly illustrates how the staircase shape reveals the independent components. Now that we have successfully found the rank in an example, let us prove why the row rank and column rank are always equal. We start by supposing we have a matrix A. and we perform basic operations to reach its simplified staircase pattern, matrix R. This chunk of the proof establishes the row rank. The mathematical reasoning here is that these basic operations do not change the underlying valid combinations of rows. Therefore, the non-zero rows in our simplified matrix R form the core independent building blocks. If we count R non-zero rows, our row rank is exactly R. This sets us up perfectly for the next step. Continuing our proof, we now look at the columns to establish the column rank. In our staircase matrix R, every non-zero row has exactly one pivot. Since there are R non-zero rows, there are exactly R pivot columns. The mathematical reasoning relies on a key rule. These pivot columns are linearly independent. More importantly, the columns in the exact same positions in our original matrix A are also independent. Since there are R independent columns, the column rank is also R. The intuition is that the pivots lock the rows and columns together. We have proven that both ranks equal R. So we have proven that rank equality holds. This brings us to an important question. Why do we care about the rank of a matrix? The most powerful application is solving systems of linear equations. The rank tells us exactly how many genuinely independent equations we have. If you have 3 variables but your matrix rank is only 2, you are missing a piece of unique information. This instantly tells you that your system will have infinitely many solutions because you lack the constraints needed for a unique answer. Let us look at how we write these systems mathematically. A system of equations can be written as the formula AX equals B. Here, A represents the matrix of coefficients, the numbers attached to your variables. The symbol X represents the unknown variables you want to find, and B represents the constants on the other side of the equal sign. The rank of matrix A acts as a diagnostic tool. If the rank increases to equal the number of variables, you gain enough physical constraints for a unique solution. If it decreases, you have a shortage of information. Before we wrap up, let us see this diagnostic tool with a concrete example. Imagine we are given a system of 3 equations with 3 unknown variables, x, y, and z. We want to know the dimension of the solution. We extract the coefficients to form our matrix A. Immediately, we can see that the second row is just the first row multiplied by 2. We perform row reduction by subtracting twice the first row from the second row, which will turn the second row into all zeros. Continuing with our system, the resulting matrix shows that one entire equation was redundant. Because one row vanished, we only have 2 non-zero rows left, meaning the rank of matrix A is 2. However, we have 3 unknown variables. Since the rank is less than the number of variables, we do not have enough independent equations to pin down a single answer. Therefore, we can conclude that this system has infinitely many solutions. The physical meaning is that our solution space is a line, not a single point. Let us summarize what we have learned today. First, the row rank and column rank measure the true amount of non-redundant information inside a matrix. Second, no matter how a matrix is constructed, its row rank will always perfectly equal its column rank. Finally, this single number is a powerful key that unlocks the behavior of linear equations. You have covered the full topic brilliantly.